Welcome to part 2 of the presentation on creating a polygonal object class and a camera class, and we'll look at a terrain capability as well. If you recall, in part 1 of the presentation, we added a camera class that had a position, look, and up vectors, had a field of view, screen width and screen height, so we could get the aspect ratio, near far clipping planes, and then the ability to do some movement and access or compute the view and projection matrices. We also created a polygonal object class that maintained its own vertex list, index list as standard template library vectors, and DirectX11 vertex and index buffers. It also maintained a transformation list, also as a STL vector of matrices. And we had the ability to add vertices, indices, triangles, transforms, and then get a composite transform, as well as creating, destroying DirectX objects, and rendering to our DirectX back buffer. So with all that capability, we now have a class that represents the camera that we can move in and out. We've got some left-right movement of the camera, rotation of the look point. We also have a polygonal object in front of us, and as we saw earlier, we can look at it in wireframe mode. I'd like to pick up where we left off by looking at the polygonal objects transformation. So notice that it's actually a list of transforms stored in an STL vector, and we have the capability of adding a transform and getting a particular transform indexed and returned by reference so that we could change it if we needed to update a rotation, for example. Also, we can get the composite transform. This is going to be that particular object's world transformation matrix. If we've got all this implemented, we'll just check at the definitions of these. So all we do is for adding, we just take the matrix and push it back in the transform list. So we just need to be aware that the transformations are going to be in order from the first one that we add will be at index 0, the second one we add will be at index 1, and so on. Getting access to it's simple enough, and then computing the composite transformation by doing a series of multiplications starting out with the identity matrix. The only thing I guess we don't have is the ability to remove a transformation or clear the transformation list. That may be useful at some point as your projects become more complex. So let's see if we can add an additional transformation maybe in our code here where we create our triangle. At some point we put in when we initialize the geometry, we put in a scaling transformation. Let's put in a rotation with XM matrix rotate, and we can rotate it by either by a particular axis or by the y-axis, and we can put it an angle, and we'll start out with 0. And the idea then is that when we go to update, remember that this matrix that we're putting in here is the second transformation. So if we want to modify the rotation of this object, we can access it by index. It'll be index 1. After we rotate it, or maybe before we rotate it, we could also translate it. Maybe we translate it 5 units down the x-axis and then rotate it. So now the rotation will be in index 2. This is the third one that we add. And we go to the update method. And we could create either a class level variable or a global variable, or in this case we could also create a static variable. And we can increment it by a little bit each time, so maybe 1 degree per second. So then we could say 1.0 times the math helper d2r, convert it to radians, and then multiply it by delta time, which is the number of seconds for this particular frame. And now instead of adding transform, we can call triangle 1 get transform, and we just need to remember that slot 2 or index 2 is going to have the transformation that we want. And we can set this equal to XM matrix rotate, this rotation Y we were using, and pass in our angle variable. So notice that the syntax may look a little bit odd. We're calling a function on the left hand side of an assignment, but we know that the get transform function is returning a matrix by reference so that we can assign a new matrix to it. And this matrix is based on an angle that's being updated. So now if we run this, it's not moving very fast at all. It's moving really slow. So, or maybe not at all. It's moving really, really slow. So I would have thought this would have moved 1 degree per second. Yeah, that's not much movement. So we might want to have it move 90 degrees per second. So it should take roughly 4 seconds to orbit around the origin. So there's our triangle moving. So this is a nice way of storing transformations in a list, and we just have to keep track of where certain transformations are in the list if we want to update them. And in a more complex project, we may put a variable like triangle 1 rotation index equal 2 or something like that to access it. So let's go and make something a little more complicated now. Instead of just a single triangle, let's actually make an object, as some of you worked on last week in the lab. In our poly object, we can call a function, maybe create something like a pyramid. And in create pyramid, we may write some code like this. So I have, best I could, tried to put a top-down diagram in a comment, and we can see that the top of the pyramid here, represented by this plus sign, is we're going to call that index 0, and it's going to be at the origin, and so X is going to the right and then Z is going up. And so we know that point 4, index 4 is, and I guess I've got the Z wrong, so it looks like that the Z actually should be over here, like this. So the Z should be like this. So index 0 is at 0, 1, 0, so it's 1 unit up on the y-axis. Index 1 is -1 in X and +1 in Z. Index 2 is +1 in X and +1 in Z, and so on. So these are the vertices that we're adding to the vertex buffer, and now we just need the appropriate indices. So I know I need a triangle from 0, 1, 2, a triangle from 0, 2, 3, a triangle from 0, 3, 4, a triangle from 0, 4, 1 to make a pyramid. And I've got a comment in here about whether we want to add triangles for the bottom of the pyramid. If the pyramid is going to be stuck in the ground and you can't see the bottom, maybe we don't need to close it. I'll leave that up to you. Depends on your application how you're going to use this. So now with this addition, we already have the rest of the code that creates the index buffers and destroys the DirectX objects and renders and transform. We just need to add and start using this class. So we can create a second poly object, pyramid 1, and everywhere we do something with a triangle, we want to do something with a pyramid. So in particular, we want to get pyramid 1's world transform and set it before we render it. So this section of code renders the triangle, this section of code renders the pyramid. We need to this is the code that creates a triangle. So now this section of code will create a pyramid, and maybe we just want to scale it. And maybe we'll scale it a little bit larger, so we'll make it something like that. We need to, we're creating the DirectX objects, we're adding the transform, and I think that might be all we need to do. It'll be at the origin, we haven't moved it. So the pyramid is going to be scaled 2.5 in the X direction, and it starts at 1, so it'll be 2.5 down. We'll make it a little bit bigger maybe. And we'll move our triangle further out along the x-axis, something like that. So we've got an issue where it looks like we're just seeing one part of the triangle. And I believe that may be in the rendering part of the poly object. So we're definitely adding triangles. When we render, how much are we rendering? I believe I found the culprit here. When we made we initialized the pyramid, we called a function called create triangle, and we need to call our create pyramid function. So now you see we have a pyramid with a triangle orbiting around it or rotating around it. And they each have their own transformation. And we can zoom in and out with the camera a little bit. So you can imagine having a collection of these create functions where you create a cube, create a sphere, create a cylinder, create a house type shape, a variety of different shapes. And you can even find objects, polygonal objects. One common format is what they call the wavefront object format. It has a .obj extension, and it's a fairly simple 3D model format that has a text version that you can actually read in the data. So you can get the specification for it, read in that data, load a model, and load it into your scene. And you can create those models and export them to that format in 3ds Max or something like Blender. The next thing we want to do is create a terrain. And we've already seen the wireframe capability. The next thing we want to do is create a terrain or a ground. You can use it for a variety of different things, a floor. Basically what we do is we set up a grid of almost like a checkerboard or a chessboard, and we have to set up a grid of the vertices. And we'll keep the grid of vertices, or the plane of the vertices, in the XZ plane, so all the Y values will be initially 0. And we'll start here and create a vertex here, and then create a vertex here, and create a vertex here, and go through a whole line of them, and then we'll go up to here and create another one, and another one, and another one. And so that will be the order of our vertex buffer. This will be 0. Doesn't want to draw 0 for me. This will be 0. This will be 1. This will be 2. Doesn't want to draw a 2 very well. Oh well. All the way to whatever the width is. So this last one will be the width in vertices minus 1, and then width plus 1, width plus 2, and we'll have several widths and heights that we need to keep track of. So we'll have a width in vertices, we'll have a width in faces or squares, we'll have a height in vertices, a height in squares, and we'll have 2 polygons for each face or each square. And we'll also have a world min and max. So we'll set up a minimum point as being here. This is the most negative value we can have in x and z. So if you think of a bounding box, that would be the negative x, negative z. That's the smallest value we could have in x, and then this is the highest value we can have in x and z. So those two will correspond to the minimum and maximum locations of our bounding box. So we can just loop through in the x direction, taking the max x minus the min x, dividing it by the number of faces, and coming up with an x value. We nest that inside of a loop that goes in the z direction, starting at negative z and incrementing it by the delta z value that's going to be the max z minus the min z divided by the number of faces. Let's take a look at how we might do that. One other thing to consider is that this set of faces is very much like a polygonal object, our poly object. So there's a couple of things we could do. The simplest maybe is that we could, instead of creating a separate class for a terrain, we could just create a function within the polyObject class called createTerrain and treat it just like any other polygonal object. Terrains often in games, though, have some special uses where you need to do some special collision detection and be able to locate things, so it may be useful to have its own class. But since there's so many similarities, we might be able to use inheritance and take advantage of functions like render and create DirectX objects and shut down and take advantage of the data members. So let's try that approach when we do this. So we'll create a new header file. And remember to put it in with our other source code, put it all together. And then we can start off by including, I'm not sure why we have this collision here. We start off by including polyObject.h and use the namespace. And then we create a terrain class by inheriting from the polyObject class. So everything that's public or protected in polyObject will be accessible in terrain. We create variables for a minimum and maximum bounding box, so x, y, z values for minimum, maximum bounding box. And we have a default constructor that we're not really going to use. We'll have a initialization function that we pass in this box min and box max value. And we have a destructor that just calls destroy DirectX objects. So now we can create a implementation file to initialize a terrain object. We'll start out by creating some variables and computing a few basic values here. In particular, what we want to do is, one of the things we want to do is loop over the terrain so we'd like to loop in the x direction and in the z direction. So I've got some variables here, I, j, k, that may help us with some looping. We compute the number of vertices as the width times the height. So however many vertices you want to cross and how many vertices you want high. And then we also pass in the min and max box values here. We also compute the width in faces and the height in faces as the width and height in vertices minus 1. Now these faces are actually squares, so probably better to change this to num squares. The height in squares, and then the number of faces, or the number of triangles, is going to be the width squares times the height squares times 2. So we've got 2 faces or 2 triangles for each square. We've got we'd like to compute what I call the delta value. So I'd like to compute the distance between each vertex in the x direction and the distance between each vertex in the z direction. So I'm going to call it delta z and delta x, and I'm going to put them in a XM float 3. So it would be nice to be able to do vector subtraction like this, but if you've seen the math presentation, we know that that's not available in an XM float 3. It's available in an XM vector, which is a 4D vector mapped to a special CPU register. So we can either do the calculation ourselves, or we can maybe overload this subtraction operator. So in Math Helper, we might find it useful to create some overloaded operators that work on vector 3s. So here is a operator plus that just adds 2 vectors. Here's an operator minus that just subtracts 2 vectors. Here's an operator times that scales a vector. You can imagine having dot product, cross product, whatever it is you need for your application. So now we're subtracting the max minus the min. We're not really concerned with the y value because it's just going to be in the plane right now, in the XZ plane right now, so y will be 0 all the time. We'll take the x value and we divide it by the width in squares, and take the z value and divide it by the height in squares. So now we're ready to start a loop and create some vertices. So the J loop is going to go from 0 to height vertices. So J is going to be going in this direction. I is going to be going in this direction. And K is, notice that K is initialized to 0 in the outer loop, but it's updated in the inner loop K is going to be for each triangle that we make. Sorry, not each triangle. K is going to be for each vertex that we make. Not each triangle, but every vertex that we make. That's what K will be for. We've already resized the vertex list to be the number of vertices, so it's already the right size. And this might help us with performance a bit if we have a large number of vertices. If you imagine a large terrain with thousands of vertices, having it pre-sized, having that STL vector pre-sized might help us with. So now we're going to, since it's already sized, we don't have to push the vector back. We can say vertex position vertex list sub k dot position equals, and then we're going to write a function called get terrain point. And the x value for this particular vertex is going to be the minimum x plus I times dv dot x. Okay? And the z value is going to be the minimum z j times dv.z. So remember, the j loop is going in the height direction and the I loop is going in the width direction. So now we're going to make a function called get terrain point, where if we pass in an x and a z, it will give us an actual 3D point. It'll compute the y and put it in a 3D point and give us an xm float 3. And then we will set the color to an xm float 4, and we can just pick whatever color we like. I think that might be yellow or something. And we finish our loops, and everything should be okay. It looks like I've got some errors. I wonder if I have an include, missing an include or something. So it looks like I might be missing a brace here on one of my overloaded operator functions. So this is okay, except I don't have get terrain point defined. What's get terrain point going to do for us? So it's going to return an xm float 3. It's going to take as parameters an x and a z value. And it's going to compute a y value. So the simplest thing to do is to create a flat terrain, so y is 0 everywhere. So that's the simplest thing to do. But later on we can come back and modify this and set the y value to some function, like maybe a sine or cosine function, and then you can have hills and stuff. Another possibility is we'll see later on how we can load up an image, and then based on the color of the image we can raise or lower the height of a vertex in the y direction, and those images are referred to as height fields or height maps. And I've even seen applications in the past where developers have gotten terrain data from the U.S. Geological Survey and actually created terrains based on real geological data of the Earth. So a lot of different possibilities for creating some more interesting terrain than just a flat. Later on we'll put a texture on it, so then if we wanted to have a floor of an inside building, it could be just flat. But I encourage you to play around with this y value and try to get something interesting. We've created the vertices, but we have not created the indices. So how are we going to create the indices? We're going to have another set of loops. We resize the index list to be the number of faces times 3. So every triangle is going to have 3 indices. We set up a loop. Again, I is going across and j is going vertically, or in this z direction. And within that loop we're going to create 2 triangles. So we're going to create a triangle from, say, 0, 3, 1, and then another one maybe from 0, 2, 3. But we have to keep in mind that the index of this vertex, this one is 0, and this one is 1, and this one is 2, and this one above it is not 2, but it is width vertices. And this one's width vertices plus 1, and this one's width vertices plus 2, and so on. So we have to do some interesting math that looks a little bit like this. So our k value is the index of the vertex index. So k starts at 0, and every index that we add will be incremented by 1. Then our first index here, 0, is really not 0, but it is the j value, which is what row we're on, times the width in vertices, plus the I value, which is what column we're in. The next vertex, vertex 3 in our diagram, is the same as this vertex plus 1 in this direction, and plus a width vertices in that direction. So it's going to be j plus 1 times width vertices plus I plus 1. So j plus 1 times width vertices gets us to here, and then plus I gets us in this direction, and then plus 1 gets us to here. So if we were right, if our I and j value, if our I and j value placed us right here, then this vertex here would be j plus 1 times the width in vertices plus the I value that gets us to the right column. And if we want to jump over 1, it's going to be that I value plus 1. If we want to go over to here, it's going to be j times width vertices plus the I value that gets us to this column plus 1 again. So that gets us index here. And then we just do a similar type of math for vertex label 0, 2, 3, again using j and j plus 1 and I plus 1. So whatever j value that we're at, whatever row we're at, we multiply that times the width in vertices. Whatever column we're at, we just use that column value, or column value plus 1 if we want to go to its neighbor. And we're looping not from 0 to width and height vertices, but we're looping from 0 to width and height squares. So remember that the number of squares in the horizontal direction is 1 less than the number of vertices, and similar in the z direction. So this sets up the index and the vertex list for us. And it's not very common that we transform a terrain. We could, but it's not as common that we do a transformation on the terrain, so we'll just set a single transformation as the identity matrix. So if we did this okay, then we should be able to create a terrain point. We forgot to return this value. Then we should be able to go to our application class and include terrain. Create a variable of terrain type. Render the terrain. Create the terrain, and remember call create terrain rather than create pyramid. And I must not have declared it properly. I declared it as a poly object. No, I didn't. I declared it as a terrain. Okay, so we called it init. And in order to initialize, we have to pass in the width in vertices, so maybe 10 across, 10 high, and a minimum and maximum box point. So if we go, say, negative 50, it doesn't matter what y is, plus 50, and do this in both the, oops, this is the minimum point, so they'll all be negative. You can do the same thing in the positive x and z direction. We've got initialize, create the objects, add a transform. We don't want to scale the terrain. We could, but we don't really. A lot of times you don't change a terrain's transform that much. and we rendered it. So let's see if we can build this and see our terrain. So now you see we have a yellow terrain that's made up of a grid of polygons, and we can extend this, make it larger, and raise and lower vertices based on some function or some data, and you make a more interesting type terrain. And then later on we'll put a texture on it, maybe grass or a rocky desert type texture, or maybe a tiled floor or something like that. For this assignment, I'd like you to modify the vertex color with some pattern somehow, and it'd be nice to have the terrain elevated or have something more interesting than a flat surface. If you want to take this a step further, it wouldn't be hard to imagine creating a box poly object and scaling it so that it's no longer a box, but it's something like a large sheet of plywood or something like that, very thin but almost looks like a wall. And then you could put several of these blocks and make a wall. You could use the terrain and rotate it 90 degrees about, say, the x-axis, and then it might be useful as a wall. So you could create a variety of different objects in your scene just by modifying the transformations and colors of the vertices and positions of the vertices as well. For the camera movement, if you look at the math presentation, we talk about how to rotate about a pivot point. It basically involves 3 transformations. We have to, if the pivot point is our look at point, if our pivot point is the camera, and the point that we want to rotate is our look at point, we want to rotate that about the camera's pivot point if we want to look up and down or left and right. And in order to do a rotation about a pivot point, which might be our camera position, we translate the problem to the origin, do the rotation, and then translate the problem, do the rotation here, and then translate the problem back to its original location. So we do a three-step process that we discussed in the math presentation. If your terrain has hills or some features in it, you may want to maintain a particular height above the terrain. So as the camera moves, you can ask the terrain what the height is and set the camera's Y value to that height. We already have that terrain, that get terrain position function done for us. Recall that when you move the camera forward and back, you not only do you want to move the camera's position, but you probably also want to move the camera's look point. You can get some odd effects if they don't move together in a certain way. So that concludes this presentation on this the second part of this two-part presentation on creating a polygonal object class, extending that to create a terrain class, and also to create a camera class with certain capabilities. Let me know if you have any questions, and I'm looking forward to seeing your scenes this week.